Hello students, today I'm going to explain you this Mobius inversion formula. So here, let me just state it here, that what is this Mobius inversion. In the class I have discussed with you what is Mobius function. I'll just recall below this statement, below this theorem, those definition of Mobius function. So the Mobius inversion formula states like this: let f and small f be two arithmetic functions related by the formula capital Fn is equal to summation of f of d, where d runs over the divisor of n. If the capital F and F are related by this formula, then what we have to show is that Fn is equal to summation of mu of d into f of n by d, where d runs over the divisor of n. So before I prove the above theorem, so let me just recall the definition of, recall number 1. Mu of n, that is Mobius function, is either 1 if n is equal to 1, and it will be equal 0 if there exists a square which divides n. And number 3 definition is that it is minus 1 to the power r if n is a product of r distinct primes p1, p2, dash dash pr, where pi's are distinct primes. So number 2, I'll recall back. Mu of n is multiplicative. I have proved this result also. That is, mu of mn is equal to mu of m into mu of n, when GCD of mn is equal to 1. Sorry, this is number 2. And number 3 is that summation of mu of d, where d runs over the divisor of n, is equal to 1 if n is equal to 1, and it is equal to 0 if n is greater than 1. So I have proved all the above result. The definition, I have defined this one. What is Mobius function? It is defined as 1 if n is equal to 1, and it is equal to 0 if there exists a square which divides n, and it will be minus 1 to the power r if n is equal to p1 dash dash pr, where pi's are distinct primes. Number 2, mu n is multiplicative. That is, mu mn is equal to mu of m into mu of n whenever the GCD of mn is equal to 1. And number 3 is summation of mu of d is equal to 1 if n is equal to 1, and it will be equal to 0 if n is greater than 1. Now, what is this Mobius theorem inversion formula? It states that capital F and small f are two arithmetic functions related by this formula. Fn is equal to summation of f of d, where d runs over the divisor of n. Then we have to show that Fn is equal to summation of mu of d, where d runs into capital F of n by d, where d runs over the divisor of n by d. This is a very important theorem. Okay, Mobius formula is an important, very important theorem on Mobius function. Okay, so here what I have to prove is, let us see the proof below. We write n here, right? N is equal to d into d prime, because d divides n. Consider d divides n. So if d divides n, by definition of divisibility, it implies that n can be expressed as a multiple of d for some d prime belong to Z. So clearly this d prime is also a divisor of n. That is, d prime divides n. Okay, so from here, write n is equal to d into d prime. So this implies that d prime here divides n. Now summation, what we have to prove is this one summation. Let me consider the right hand side of this. summation of mu d into f of d, I have to show that this right hand side is equal to, I have to show that this one is equal to fn. So let me consider the right hand side. So now summation of mu of d into f of n by d, where d runs over the divisor of n, is equal to summation of mu of d into, where d runs over the divisor of n, into summation f of c, where c runs over the divisor of n by d. Why? Because f of c, because capital Fn here is related by this formula summation f of d from the statement of the theorem, d divides n. Okay, so if ffn, let me go back to the statement. See, small f, capital F and small f are related by this relation. So this capital F of n by d, I'm going to express it in the form of summation of f of d. But here you have f of n, and here you have n of n by d. So I'll just show you. Since f of n is equal to this, so this implies that f of n by d will be equal to summation. Now I'll replace it by f of c. Okay, here you have n and here you have d, where d runs over the divisor of n. Now here you have n by d, and here this is summation of f of c, where c now runs over the divisor of n by d. I'm just replacing this n by n upon d and this d by c, and here this d now becomes c, and n here will becomes n upon d. So that's why this f of n upon d is equal to summation of f of c, where c runs over the divisor of n by d. Now this is equal to double summation this one and this one, okay, where d runs over the divisor of n and c runs over the divisor of n by d, mu of d into f of c. Now, from definition of divisibility, d divides n and c divides n upon d. This is true if and only if c divides n and d divides n upon c. How we get this? It is because of this. Okay, let me just go below. See. Now d divides, c divides n upon d. Okay, c divides n upon d. It implies that c divides d prime. What is n upon d? We consider from the beginning of the theorem, n here is equal to d into d prime. So clearly d prime divides n. So I'll replace this n upon d. Okay, this n upon d. Let me express it. We have n, we consider n is equal to d prime. So this implies that d prime here is equal to n upon d. So clearly d prime divides n. Okay, so c divides n upon d, but what is n upon d? It is d prime, implies that c divides d prime because d prime is equal to n upon d. And what is d prime? D prime here, this d prime, n is a multiple of d prime, so clearly d primes divide n's. And since d prime, okay, divides n, c divides d prime and d prime divides n, it implies that c also divides n. So therefore d divides n, c divides n upon d if and only if c divides n. Also, we have by this relation c divides n upon d implies that n upon d is equal to, because c here divides n upon d, it implies that n by d is equal to c times into, say, some positive integer k, means that n by d is a multiple of c. So which implies that cross multiply n upon c is equal to d into k. So which implies that n upon c is a multiple of d, which means that d divides n upon c. So therefore, D divides N and C divides N upon D if C divides N and D divides N upon C. So I'll replace this in the above equation. Means this is equal, now this will change to D divides N, I'll replace it by C upon N, and C divides N upon D, I'll replace it by D divides N upon C. So therefore, the above summation now becomes summation D divides N, I'll replace it by C divides N, and this C divides N upon D, I'll replace it by D divides N upon C into mu of D into F of C. So this can be written as summation of F of C with this, where C runs over the divisor of N, into summation of mu of D, where D runs over the divisor of N upon C. So now let us see what is this. As we have seen in the previous result that I have discussed in the class, what is summation of mu of D, where D runs over the divisor of N? It is equal to 1 if N is equal to 1, and it will be equal to 0 if N is greater than 1. So using the above result here, so let me name this as equation 1. And what is the right hand side? It is summation of mu of D into F of N upon D, where D runs over the divisor of N. Okay. So now this part, now we know that, okay, I'll just write below. Now summation of mu of D, I'm considering this, okay, this and this, summation of mu of D, D runs over the divisor of N upon C. This will be equal to 1 if N by C is equal to 1, and it will be equal to 0 if N by C is greater than 1. Why? Because we have this relation, summation of mu of D, D runs over the divisor of N. Since we have proved this result, it is equal to 1 if N is equal to 1, and will be 0 if N is greater than. So you just replace this N by N upon C. So therefore, this will be equal, summation of mu of D will be equal to 1. So if N upon C is equal to 1, it implies that this implies that D which divides N upon C, and this is equal to 1, it implies that D must be equal to 1. So therefore, this equation is equal to summation of F of C, where C runs over the divisor of N into 1, because this value is, as you can see here, from the result we have proved, it is either equal to 1 if N is equal to 1, or it is equal to 0 if N is greater than 1. But in this case, we have N upon C, so it means that it will be equal to 1 if N upon C is equal to 1, and it will be 0. So the only divisor of summation of D here is equal to 1 will be, so this whole thing will be equal to 1. So which is equal to summation of F of C, where C runs over the divisor of N. C runs here the divisor of N. So this is equal to F of N. Okay. What are the divisors of N? So here C runs over the divisor of N. So it will be F1, F2, Fn. So there will be Fn terms here. So we will replace it by F of N. So thus we have F of N here is equal to summation of mu of D into F of N upon D, where D runs over N, if capital Fn is equal to summation F of D, where D runs over the divisor of N. So this is called the Mobius inversion formula. So sometimes they used to ask, even this year, last exam also, they asked state and proof. This is Mobius inversion formula. So sometimes they used to ask the question which used to come is state and proof. Question which comes regarding this Mobius inversion is that state and proof Mobius inversion formula. So state and prove Mobius inversions formula. First you give the statement, and what is the statement is that if capital F and small f are two arithmetic functions related by this formula, Fn is equal to summation of f of d, where d runs over n, the divisors of n, then Fn is equal to summation of mu of d into f of capital F of n upon d, where d runs over the divisor of n. So that is a statement, and the proof you have to give there, how you get this result. Okay, so I hope it is clear. But let me just give as a remark below this. Okay, as a remark, number 1. Okay, let me write it first. If capital Fn is related by the summation f of d, where d runs over the divisor of n, then this is the Mobius inversion. Then f of n here will be equal to summation of mu of d into capital F of n upon d, where d runs over the divisor of n. So the result we obtain from this Mobius inversion is number 1. Tau of n. What is tau of n? It is summation where we add 1 to each divisors of n. So here you take this capital, since this one capital F of n here, you consider it as tau of n, and small fn is equal to 1. So therefore, by the above relation, we have Mobius inversion. You replace this fn by 1 here. This is summation of mu of d into tau of, if capital Fn is called tau of n, then f1 by d will be tau of n by d. So which is same as, according to Mobius, this is same as mu of n by d into tau of d, where d runs over the divisor of n. So how this Mobius is related to tau and sigma. Number 2 is sigma n. It is the sum of the divisors of n, where d runs over the divisor of n. So here you take capital Fn is equal to sigma n, and f of n here, which is equal to small n. So therefore we have n here, substitute in the Mobius formula, n into summation of mu of d into sigma of n by d, which is same as summation of mu of n by d into sigma of d, where d runs over the divisor of n. Actually, this Mobius inversion, the statement, where is the statement? Okay, I'll just write here. This is same as summation of mu of n by d into tau of into capital F of n, capital F of d, where d runs over the divisor, and you just have to replace this d by n upon d, and this n upon d you replace it by d. So Fn here is same as this. So this is also the formula for the Mobius inversion. Okay, I hope it is clear. That is, if capital Fn and small fn are related by this formula, capital Fn is equal to summation of f of d, then we have Fn is equal to summation of mu of d into f of n by d, where d runs over the divisor of n, which is same as summation of mu of n by d into f of d, where d runs over the divisor of n. So what we have done, I'm just recalling those results that I proved. We know that from the definition of Mobius function, it is defined as 1 if n is equal to 1. It is 0 if a squared, if there x is a square which divides n, and it will be minus 1 to the power r if n is a product of r distinct prime. And we have proved this, the results below also, that is mu n is multiplicative, and summation of mu d is ad equal to 1 if n is equal to 1, or 0 if n is equal to 1. So with the help of the above results that we have discussed in the class, so we are going to prove this. These are the proof of the Mobius inversion formula. So you write n is equal to d into d prime by consider d divides n. So d divides n according to definition of divisibility, it is equal to d into d prime for some d prime belong to Z. So clearly this d prime is also a divisor of d, because it is a n here is a multiple of d, or you can say that it is a multiple of d prime. So this implies that d prime divides n. Now consider the right hand side of that formula, summation of mu of d into f of n by d. But what is the relation of capital Fn with small f? It is defined as Fn equal to summation of f of d. Now if you have n upon d here, then this replace this d by c, so that you have c divides n over d. So by replacing it, now you get this double summation. D runs over the divisor of n, so double into summation of where c runs over the divisor of n upon d, mu of d into f of c. Now we know that d divides n and c divides n upon d if and if c divides n and d divides n upon c. And how we get this result is, as you can see here, c divides n upon d, but we know that n upon d is equal to d prime, so implies that c divides b prime, but d prime here divides n, since it is a multiple of n, so this implies that c also divides, and from the one of the basic properties of divisibility. Also, c divides n upon d implies that n upon d is equal to some multiple of c, that is c into k for some integer k. Now you just cross multiply, so n upon c will be equal to dk, which implies that d here divides n upon c. So therefore, we have d divides n and c divides n upon d, if and if c divides n and d divides n over c, which is equal to this formula. Now c divides n, you write first into summation of mu of d into f of c. You replace this d upon n by c upon n, and d divides c over d here. So therefore, this f of c in summation of f of c, where c runs over the divisor of n, into summation of mu of d, where d runs over the divisor of n upon c. But we know that the value of summation of mu of d, I have proved the result, that is summation of mu of d is either 1 if n is equal to 1, and it is equal to 0 if n is greater than 1. But instead of n, here you have n upon c. It means that if n is by c is equal to 1, and it will be equal to 0 if n by c is greater than 1. So therefore, this whole summation will be equal to 1, which is equal to summation of f of c, where c runs over the divisors of n, and this whole summation is nothing but f of n. So this give you the Mobius inversion formula and its proof. Okay. And some of the remarks also I have given here. So I hope it is clear what is Mobius inversion. So if during exam they ask you state and prove, you have to give the statement and then prove it.